Well, artificial intelligence. You have it, in fact, in all your smartphone. You have a lot of artificial intelligence around you, and this is a topic which is developing extremely rapidly. And what you can see here is two persons facing each other. The one is the human personality with a normal brain on the right, and on the left you can see an artificial human. And the question is, how long will it take until the artificial human, or the robots, or the machines will take over? And this is exactly the topic of this question which I'm raising about the technological singularity. Vingo Vinge is a scientist who wrote science fiction novels in 1993, and he was based on the development of artificial intelligence, claiming that maybe in 2035, this was already in 1993, in 2035, in fact, the human might be completely overrun by artificial intelligent machines. So this is something which is a bit triggering, of course, and asking ourselves, is it really going to happen? And I'd like to bring you on a little trip here and first discuss the idea of the robots. Will machines and robots surpass all human intelligence? So you see here a lot of progress has been done with robots since the early years in the middle of the 20th century, when you see on the left robots of Saturn. And then you see now that you have robots with are humanoid. They have shapes of humans, and they are developing themselves very quickly. I think a lot of groups in the world are trying to make such robots and making robots which would be, in fact, helping us in different tasks in our everyday life. Now we go even a step further now. You can see robots which look like humans. They have a skin, they have eyes, they can even show expression of their face. They have a mouth which can move the lips at the same time that it speaks. But this is still a robot. Inside, if you look, you will have a computer, and you have all sensors and activators making the whole thing working. So the question is, should we be fair? Should we have some anxiety about the developing of robots? And you can see here 3 examples of films which are portraying artificial intelligence. And the first one is the famous movie by Stanley Kubrick, which is 2000: A Space Odyssey. You have seen it certainly. It's an iconic film where the computer HAL 9000 at a certain point get out of control. And the scientists on the spaceship tried to turn it off, but the computer, he could read at a certain point on the lips of the different scientists in the capsule, and decided to work against the scientists. And finally, he was really not obeying anymore the orders of his people. And so this is a very interesting thing, because the robot HAL 9000, if you think about it, Stanley Kubrick took these 3 letters, and if you take the following letters after each of them, you will see that it's IBM. H, the letter is I, A is B, and then L you will have M. So already in 1968, he was using IBM computers to think about this. Now you can see other themes like robots, NS5 robots, which is iRobot, or Ex Machina. There are many, many different movies which are showing, in fact, the threat of robots which might be killing or even destroying their own creators. And this is something which I believe has developed among the public, a lot of open question about artificial intelligence, but also about killer robots. You see here the example of killer robots coming in the movies, and we are facing really with bad expressions. But the question is it only science fiction? And if you look on the bottom, you see a drone or an autonomous killing machine, which is a gun, could be running autonomously. And this is something which is raising a lot of ethics about what are we heading if the robots will be killing other people. And this brings me to the 3 laws of robotics, which were written in 1942 by Isaac Asimov, in his short story, Run Around. And you can see the first law says a robot may not injure a human being or through inaction allow a human being to come to harm. So this is already in contradiction, which I've shown you before. The second point, a robot must obey the orders given it by human being, except where such orders would conflict with the first law. I mean, of course, a robot, you can give him order and he might kill somebody else. The point is also, the third law is a robot must protect its own existence as long as such protection does not conflict with the first or second laws. So, of course, these laws, which were written in 1942, at the beginning of the artificial intelligence, are now a little bit outdated in the sense that all type of robots will be getting out of control. A survey has been made in the UK trying to find out what is the feeling about artificial intelligence among the public. And you can see that 67, which means 2/3 of the Britons, are worried that artificial intelligence will result in machine taking people's job. This is already a very important issue. 59% are very nervous about the way their personal data is collected and used since the rise of artificial intelligence. Even worse, if you look at 24% even think artificial intelligence could be responsible for the end of humankind. And finally, 62 are still believing that artificial intelligence might still be good for and will not harm anybody on the world. And finally, 37 people admit that they don't fully understand what it means. So I don't know in what category you are and what do you want to answer yourself. You can make some kind of a quick answer to this survey. So the question is, what is artificial intelligence? And the main way of saying it is the creation of intelligent machines that work and react like humans. What I was showing you, these robots which can think, which can have perhaps in the future some feelings, some emotions. And one important issue for a robot to be like a human, he has to be sensitive or knowledgeable about his own existence. And this will, I believe, take a long time until this happens. So I would say we should not use too much the word artificial intelligence, but maybe use more machine intelligence or augmented intelligence. And artificial intelligence, or if you wish now machine intelligence, is holding 3 items: the machine learning concept, the neural network concept, and the deep learning, which produce all together what we call today computing, cognitive computing. To understand the deep learning, this is a subset of machine learning, and this is something which you have to look at this diagram. On the top, you see there is a car, and a computer has to find out that the car is really a car. It has to decide on that. But this is, in machine learning, it needs the help of an expert who is taking the extraction of the data and putting the data in the computer, and then the computer is taking classification and finally will say, yes, this is a car. So this is the simple machine learning, which has been running for quite many years. The deep learning is something which happens without the help of a human being, of an expert. So you see that the car, you have an input, it gets in for the different network layers, and then the classification and the extraction are all done together, and finally the computer can tell you it's a car. The deep neural network. This is something very interesting. You can see that on the bottom you have a picture of a woman's face, and the computer will take this picture and make 2-dimensional layers of it with many pixels, and then we'll go into the first layers of nodes, which could be neurons or artificial neurons, and then you will have a transmission from all this first layer to the second layer, third layer, and fourth layer. And this is in the hidden layer number 2. You will see that the computer is only analyzing the different edges, looking at the face where you see the black and white edges. Then in the second layer, it will go and look at the configuration of these edges, trying to put these edges together and making something like an eye or a mouth. And finally, in the third layer, which is the hidden layers, it will look at object models, which looks already like faces. And finally, the output will be the face of a woman. If we look at the founders of the artificial intelligence, I'd like you to remember at least these 5 names. The first one is coming back in 1805, where the mathematician Legendre invented Adrien-Marie Legendre, a French physicist and a French mathematician especially, invented the first statistical principle used by machine learning algorithm today, and basically developed the least square methods, which is used for linear regression and curve fitting. Also very famous is Norbert Wiener, which is the father, if you wish, of cybernetic, a way of using feedback techniques implemented in programming. And he was a very important scientist contributing also to the development of artificial intelligence. The next one is Alan Turing. You all know about Turing has been the one who decrypted the Enigma machine during the Second World War, and you have several movies which have been done on him. And I believe he's one of the father of very important of the artificial intelligence and also of computing programming and using algorithm. Then you have John von Neumann, a very, very productive Hungarian and American mathematicians who have basically described the architecture of the computer. It's why we call today a computer as a von Neumann architecture. But of course, he developed many different theories in mathematics. And finally, Claude Shannon, who is in fact the father of information theory, who has been also contributed at that time. This is all things happening between 1940 and 1950. And the beginning officially of a conference of the artificial intelligence is shown by this first conference which took place in Dartmouth College in 1956. And then the history of artificial intelligence have developed dramatically. There have been even some winters in the 70s and 80s because there was not so much money available. People were thinking that the computer will never achieve enough performance to go on with artificial intelligence. And it's essentially starting in the 90s that it took off by the fact that the computers were stronger and stronger. So today, artificial intelligence impacts all industries. Health, we have heard before. I mean, what can happen, what we can do with maybe nanorobots get into action, into financial services, manufacturing, logistic, education, agriculture. And so the semiconductor industry is very much interested today in developing these techniques in all these aspects because there is a lot of money involved in these things. So the foundation of artificial intelligence are 3 pillars. The data, which you need to analyze, the algorithm, which are basically a set of logical instructions which makes the backbones of a program, and finally, the computing strengths of the computers. And if you look at this, the data, this is the workload for artificial intelligence, and you can see on the top, text analysis. You need really to make correlation between the words in order to find a sense to a text or to written information. Or you have object detection. You see the players, which are followed by the little square, so this can be detected very nicely, or the face detection of people moving in a team here in basketball, but it could be everywhere in your life in a city. Now you need also to develop new architecture. This means the computers and the hardware has to be developed in a very systematic way, what we call also heterogeneous integration. And then you need to develop the networks and the algorithms, which are basically related to the software part. And this has to be developed all together to make a successful artificial intelligence. So now we distinguish between narrow artificial intelligence, which is the initial value of creation. I mean, you see that this is basically the simple machine learning, which I was describing before. You can detect a cat among different pictures, or you can detect faulty medicine or pillar if you can analyze pictures this way. So this is something which developed essentially between 2010 and 2015. On the other side, you have a so-called general or strong artificial intelligence, which is the revolutionary part of it, where, as I said at the beginning, robots might take over and might be becoming very intelligent. And in the middle, you have a so-called broad artificial intelligence, which is what we are today, with, again, financial analysis used in the basically industry and, again, in healthcare, diagnostics. And this is a very important point where the learning is adaptive using automatically constructed architecture. So in this level, this is kind of things you want to understand is a comprehension of a picture. Here, this is a parrot which is in a cup, and there was a contest where a computer had to find out and be able to describe what he was saying, a green bird sitting on top of a ball. Or the other things which is important is learning and reasoning from scalable machine learning to make a case. It means that if you understand a discussion, you want to make a sense out of the discussion. I will come back to this. And finally, you want to investigate the language, but also the emotion of a person which is photographed. So all these things are basically things you can do today. And one very nice example is the IBM project debater, where a computer can debate, exchange ideas, and in fact, on very complex topics, have a very well-structured speech with a human. And there are several pioneer capabilities you can read there of a data-driven speech, writing and delivery, listening and comprehension, and ability to model human dilemmas and form rational arguments. And this is in some way a very important milestone for IBM to do this. You remember that the Deep Blue was the first computer which have beaten Kasparov in chess playing, or in 1911, the development of Watson, which was a computer which could win against the champion of Jeopardy, which is a game in the United States. All this was possible because there have been a strong development of the evolution of information technologies. You see, with the years starting in 1900 and up to today, the increase of a number of computational that you can do per second, or you can buy in some way, has been increasing from the mechanical, electromechanical vacuum tubes, which were discrete entities, the transistors, the integrated circuits, and today the nanotechnology, which is allowing to make things at the nanoscale and bring this very, very powerful computer that we have today. And one of them is the Summit, which is not the worst, but the world's most powerful computer for artificial intelligence. It has power performance of 200 petaflops, which is 210 to the 15 calculation per second. And also it has a huge amount of control processing units. You can read them. They are also using graphical processing units, and it uses a lot of energy, 13 megawatt to run this computer. And the price is around $200 million. Now you can go on the other side and make the smallest computer. And the smallest computer is also a computer which has been developed at IBM. And this is something which is very interesting because it has the size of 1 millimeter square, so the size of a grain of salt. You can see it on the right. And also, it has a lot of self-management. It has solar cells to provide enough energy, and it has the performance of a processor of the 90s. You might all remember the Intel 386 processor. And the manufacturing cost is very, very low. So you can use it for cognitive computing everywhere, for edge computing. It means all the devices which are interacting, and also for blockchain and crypto anchor. So now, there are two challenges for artificial intelligence. The first one is the explosion of data. As I mentioned before, you are producing mega numbers of data. You can see here by 2022, there will be over zettabyte, I mean 10 to the 21st of data will be produced. 90% will be machine generated. There will be a huge proliferation of data because of the Internet of Things, which you can see on the right, the connection of all these devices from the smartwatch, for the smartphone, the autonomous car, and so on. So we are running into a huge amount of data which are produced, but also the second point is the energy demand. And the energy demand and the efficiency needs to be very much developed and kept under control. You see, for example, that new artificial data centers could consume more than 10% of the global electricity supply by the year 2025. And also that it contributes quite a bit to the greenhouse gas emission. So we need to improve the performance, the efficiency, and find new technology. And this is where it leads us to neuromorphic computing, or so-called also analog computing, and quantum computing. I will not talk about quantum computing today, which is a very important issue, a very important development in computing, but basically only about neuromorphic computing. And neuromorphic computing is basically something which is working like the brain. And you see that it's an analog computing. The brain is not digital. It basically spikes which are moving into the brain. And this is, if you wish, you can compare a digital watch to an analog watch. And this is what we are trying to do nowadays in order to save energy and also to be faster. You get something back to analog because it needs maybe less precision. No, the precision is infinite, but the accuracy can be approximate. So the point is that you go away from the bits, which are 0, 1, 1, 0, and so on, which are used in conventional computers, and then you use signals, which can be a voltage or a current produced by sensors and so on. So in some way, we are getting into using these specialized accelerators to make a computer faster. And the idea there is really to get rid of this so-called von Neumann computing, which is the von Neumann bottleneck, where on the left you see that the data which comes into the computer are controlled by the CPU, but in fact all the data is moving back and forth into the memory, which is taking a lot of energy and also a lot of time. And now the idea is to use the second approach to have a computing directly in the position of the memory, and you call this a computational memory. So the input data produce results directly, like in the brain, where you have the storage of the data and at the same time the controlling of them. So this is bringing us to the fact that you want something which is like a brain, neuron-based networks, and you can see that brain is made of dendrites. I mean, the neurons, which is made of dendrites. You have a nucleus, you have a soma, and then you have the axon, and that all the message is transmitted across this neuron using the synapses as being the connections between these neurons, which is basically shown here. All these are the synapses which is connecting one neuron to the next one. So the neurons are getting spikes. The spikes are getting into the dendrites, into the cell body, which is shown here. And then if there is enough of correlation between these spikes, you will have some firing, and the axon will transport the information out of the neuron. And what we are trying to do today is to use so-called neuromorphic crossbars array, which are shown on the right. These are basically perpendicular conducting layers, lines. And between these lines, you have a device which can be switched on and off, as shown here. This device can be a resistance which can be taking the different values. So the red, it's closed, the green, it's on. You have a presynaptic entrance, and then you have the output coming out. And this is a very important new architecture using these crossbar arrays. in the sense that you can basically exactly use what I've shown you before with these deep learning networks. You have layers of neurons on the left, which are linked to the second lines of neurons, which are the second columns, the black dots, and they are connected by lines which are called the synaptic weights. And the intensity of this light is telling you how important is this weight. So you have neurons and the weights connected, and you go from one layer to the other one in a so-called neural network. And this is translated into this so-called crossbar memory exactly in a very simple way. You can see that the neurons have a color which is rose, the rose's color, and then the first layer on the left are getting into these different synapses which are in blue, and these synapses are formed in this crossbar array, and the output on the bottom are the neurons which are the second layer which is shown on the left. So you can basically use this architecture and work out a computation which is directly located to the memory. And to do this, we have several techniques, and one which we are using here is so-called phase change memory. This is a material which can change its crystalline structure in an amorphous structure when you let a pulse of current getting into it. And you see that this mushroom, which is shown on the left, can go up and down. And if it's growing like it is now, the resistance of this device will be high. The electrical resistance will be high, and if you decrease it, it will be very low, because the ordered structure of your lattice has a much better conductivity. So this is shown here. You see on the left, on the right, that if you have a resistance, which is shown there, and you have fully crystalline, the resistance is very, very low, which means the conductance is high. And when you increase the mushroom size, you can, by applying different reset voltages, you can make it going up and the resistance increase. And you can do the opposite on the other side. And in this way, you can change the synaptic weight of your devices, and this allows you to make all this calculation, as I mentioned, at the level of the memory. I don't want to go into the details because this is rather complicated, but the material which is used is something based on germanium, antimony, tellurium, or germanium, antimony. These are type of chalcogenides which are actually used for this type of device. Now we'll finish with a few slides which are showing an application of this type of neuromorphic computing. Is it shown here? On the left, you have an array which is describing, let me see, here, this is a letter. This is a number. It's in a 28 by 28 array, and this numbers is a handwritten digit which can be seen here. All these digits have been tried and been put into a database, and the system has learned to detect out of all this example of different digits what one should be the right one. And then you transfer this information through first layers of neurons, which are real neurons based on this phase change memory, which I was showing you before, in a second layer and in a third layer. And finally, the signal at the output for different process will tell you, okay, this is something like a 5. So it will show you the 5. So this is something which has been devised in our laboratory. And it's basically a device which is shown here. This is the center, the core of this whole thing. So of course, you need to have some output and input with the normal computers. But this is basically the heart of this neuromorphic part. And I just want to show you now what you can do with this. If you write an 8, this 8 will be detected by in the array of this system, and will be transmitted to the first array, which is 740 times 250 digits. and then it will be transmitted through an integration process to the second array, and finally you will get at the end the number 8. So if I try to get to this running, so it's just basically writing this 8. It could be a 7, it could be any kind of other digit. And then you see you can make either a run on the real machine or you can make a simulation. The whole system is working out through this different level of neurons. And then finally, you get the data out, 8 coming out. And this is something you can, in fact, go on the webpage of IBM and try this experiment on your own, trying to find out if your writing of the digit is recognized by the computer. Okay, so this brings me to the end, and basically the conclusion is the following. Artificial intelligence is everywhere today. It is in your smartphone. It is in many other applications that you can see. Today you can do application like generating new medicine with artificial intelligence. We can also produce perfumes, taking among thousands and thousands of molecules, picking up the best molecules to produce perfume, which has a very specific profile, for example. So artificial intelligence will be a very strongly developing process, and it will get into the broader intelligence. Artificial intelligence will permeate every discipline and all industries, from finances to manufacturing and to healthcare. And analog computing, which I was very quickly showing to you, is removing the so-called von Neumann bottleneck. I mean, this transfer of data between the CPU and the memory. And finally, neuromorphic computing with this phase change memory will be a key solution for deep learning, as I showed you in a very brief manner. So, yeah, artificial intelligence is the new IT, the new information technology, but the technological singularity, which I was talking to you before, I think it's still far away. The only thing people might say, maybe it's not really artificial intelligence we're talking about, it's also about artificial stupidity. Because it will depend, the evolution of this will depend very much on how we humans are dealing with artificial intelligence. Can we control the development of these robots I was talking to you about? Can we make limits? Can we set up some new laws about using artificial intelligence? So I believe that there will be a drastic change in our behavior in the future, but I still hope that the human will keep the overhand on the development of computing science, on the development of technology in the sense of keeping up with society where the relationship between the human people, the ethical aspect will be preserved. And I would like to finish here by thanking you for your attention.